Hi, and welcome to this session on how Sony Interactive Entertainment renders with AWS. My name is Peter Hennebeck, and I'm a Solutions Architect with AWS, and I'm joined today by Asghar Nisar, who's a Project Manager with Sony Worldwide Studios IT, and has 10 years experience in delivering cloud-based technology services, and is responsible for cloud adoption strategy and cloud excellence at Worldwide Studios. I'm also joined by Andy Taylor, who's a systems engineer with over 10 years experience delivering technology solutions for Worldwide Studios. Today, Asghar and Andy will tell you about how Sony uses AWS to render video motion graphics. But before I hand over to Asghar and Andy, I want to talk a little about some of the AWS services and tools our customers can use to run graphics workloads in the cloud. The Render Farm Deployment Kit, the rfdk, is an open source software development kit that can be used to deploy your graphics render farm in the cloud. The rfdk is built to operate with the AWS Cloud Development Kit, the CDK, and provides a library of classes that lets you deploy and configure your infrastructure as code. With the rfdk, you can set up the VPCs and networking to deploy cloud-based render farms with high-performance storage, such as Amazon FSx for Windows File Server and FSx for Lustre, in combination with object and archive storage using Amazon S3 and S3 Glacier. You can also use accelerated compute instances, such as EC2 G4s and P3s, and take advantage of GPU accelerated rendering for the most complex graphics. Using the rfdk to deploy AWS ThinkBox Deadline, customers get the elasticity of cloud infrastructure with the stability of infrastructure as code. And crucially, the rfdk and CDK are built with security as a top priority so that your render farm is built on a secure foundation. And with that, I'd like to hand over to Asghar and Andy, who will take you through how they use Deadline and rfdk and some of the tweaks they use to get the most out of GPU instances.
Thank you, Peter. Hello, everyone. I'm Asghar, and I'm a project manager for Worldwide Studios IT. Worldwide Studios is a global network of development studios that is part of the PlayStation family and makes exclusive games for the platform. Worldwide Studios IT provides technology services that are tailored to meet the high demands of game production. Put simply, we support Worldwide Studios in making great games for the PlayStation. Render is a critical capability for our studios, particularly in the production of motion graphics, where all work streams converge at render. Therefore, any reduction in render time adds slack to the production process, and conversely, any increase in the render time adds contention. In this instance, our creative services team needed to produce motion graphics content urgently for a recent global press event. However, the additional processing power needed to sustainably render next-gen visuals at 4K 60 meant our on-prem render farm reached its full capacity very quickly. This resulted in long render times, job contention, and led to a production bottleneck. The creative services team was at risk of missing their deadline, and IT needed to make the render farm go faster. We decided to turn to the cloud to relieve our on-prem render farm of its heaviest workloads. The nature of the cloud made the decision to invest in AWS easy. Capacity is abundant, and pay-as-you-go pricing negates capital expense and procurement time, removing our biggest constraints: capacity, cost, and time. This flattened the risk and allowed us to get to work immediately. The core principles we followed to steer the project were twofold. Firstly, to align engineering choices with the challenge and user experience, meaning that the solution must be fit for purpose, mainly to overcome the challenge, and fit for use, mainly to accommodate the creative services team's workflow and software suite. Secondly, and most importantly, to uphold service excellence. This is the underpinning constant in everything that we do, and in this context, it means fast, secure, affordable render. The outcome of the project surpassed our expectations and allowed us to render affordably at 12 times the speed of our on-prem render farm. This allowed the creative services team to meet the event deadline, and as you can see from their feedback, they were very relieved. This yielded instant return and validation on our investment in AWS. I'd like now to turn to Andy for a deep dive into the solution engineering.
Hi everyone, my name is Andy Taylor and I'm an engineer at SIE Worldwide Studios. Today I'm going to do my best to take you on the journey that we embarked upon with AWS to move our motion graphics rendering into the cloud. Now at the very start we had some very high level engineering goals. Now firstly, as it should be, we needed a secure solution. A solution that could align with our InfoSec mandates. We needed the ability to customize the deployment so we could fully provision it within our private VPCs, knowing fully we could take advantage of Direct Connect for private on-prem access. Next, we wanted to really realize that provisioning dream where we wanted to be able to deploy and manage our infrastructure with just a few commands when our creative team said go. And conversely, we needed to strip the infrastructure back down to when that demand was fulfilled. And of course, we ultimately wanted to leverage the elasticity and scalability of the cloud to address our render compute requirements. And finally, we wanted to use AWS for our heavy lifting. And this meant processing 4K 60 render jobs that relied on GPU processing. And in our case, using Maxon Redshift. And this directly aligned with our creative team's vision to move from an existing slower CPU rendering solution to a faster and more scalable GPU solution, leveraging Redshift. Now, based on these goals, we had to make a number of informed engineering choices. And I'm going to run you through the 5 most critical decisions that shaped our success. Firstly, we decided to deploy our infrastructure as code using AWS CDK. And with the help of AWS ThinkBox, we were able to put in place a custom CDK application that deployed all the necessary AWS infrastructure to create a deadline-based render farm. So we defined 5 stacks, like you can see in this diagram. That's 5 Python files which could be deployed independently, so we could build the infrastructure in layers. And this meant using CDK deployment, we could have our deadline and all the supporting infrastructure up and running in 5 commands or less. And equally, of course, that meant we could strip it back with an equivalent number of commands. Now the first 3 stacks are primarily standard AWS CDK constructs, which are provisioning us all the necessary network and storage infrastructure. We have a standard VPC architecture at Sony, and with the network stack, we were simply able to define our existing VPC IDs and subnet IDs and just do that once and have those persist throughout the application. And that for us was a real time saver. Now, our identity layer implements AWS Managed AD, and that supports our choice to deploy Windows Server for our render nodes and also enables authenticated access to FSX for Windows File Server. Now within the service stack code, we start to combine rfdk constructs in our CDK code. And this is where we install and configure deadline. Now finally, we do some admin in the compute layer with both CDK and rfdk to define some AWS groups and some deadline specific groups. Then all we have to do to deploy a stack of infrastructure is run CDK deploy and then the stack name. Now you'll have to write the CD application yourself in Python or NodeScript, but the good news is there are plenty of examples at the rfdk GitHub site and some good getting started guides within AWS documentation on rfdk. Now, as I mentioned in the previous slide, in the service stack we start to introduce rfdk constructs. Now the render farm deployment kit, as Peter said, is a complete library of software constructs that enables you to define, deploy and manage your deadline render farm. So all we needed to do to deploy the deadline components of our infrastructure, so in this case the render queue, the repo and the database, is define the properties of those components and then call the associated rfdk construct in our CDK code. And what's really useful to keep in mind here is that when a CDK stack is deployed, all of your familiar Python code is compiled into CloudFormation templates. And when you see the sheer weight of that CloudFormation template, it's clear to see that a single rfdk construct is a very powerful tool. You'd have to do an awful lot of work if you were going to write this in native CloudFormation templates. So in this proof of concept deployment, we used a beta version of rfdk. Now these older constructs reference specific AMIs to build EC2 instances and relied on configuring some AWS services in advance of calling the rfdk construct. Now since rfdk has become generally available, it will deploy you all the necessary AWS resources without explicitly defining them with CDK constructs within your CDK stacks. Now, as a result of our CDK and beta rfdk deployment, we provisioned and configured all the necessary AWS and deadline services. You can see here in this diagram in the center, we have the remote connection service installed and it's configured. And that's a single point of connection for deadline client components, and that's via an application load balancer. Mounted on the remote connection server is AWS EFS with a configured deadline repository and an instance also of MongoDB running the deadline database. You can also see there we've got a deadline usage-based licensing server, and as part of the GA version of rfdk, that is deployable with a single rfdk construct. We've also got managed AD, FSX, and our Spot Fleet render workers, and they all work in harmony to give us a familiar framework of secure file transfer over SMB, and of course that reassurance that all of our CIS InfoSec mandates can be taken care of with group policy. Now what about our on-prem artists? Well, they have secure private connectivity and they leverage Direct Connect from our on-prem networks. And they are able to submit render jobs to our Deadline farm from Cinema 4D directly, and that uses the Deadline C4D extension, and we can submit and monitor jobs also from Deadline Monitor. Now, we made the decision to deliver our render workers using P3 and G4 instances. We had a CUDA application that needed CUDA cores. We necessarily didn't need WDDM or the ability to fire up 3D apps. We just needed Redshift to have exclusive access to the GPUs. And because of this, we were able to use the NVIDIA Tesla driver for both the P3 and G4 instances. Now both drivers will install in TCC mode, which configures the graphics cards solely for compute. Both P3 and G4 provide us up to 16 gig of RAM to allow loading of complex scenes and textures. And next up, both P3 and G4 provide us that multi-GPU scalability, so we can assign up to 8 GPUs per instance with the P3 instances. Now Redshift out of the box supports a maximum of 8 GPUs, and with the P3 16X large, we're able to provide 8 NVIDIA V100s, and that's nearly 41,000 CUDA cores per instance. And because we're paying for Redshift render license by the minute, the option to scale up to 8 GPUs ensures that Redshift is working as hard as it possibly can for that license cost. We then chose to deliver our Deadline render workers on Windows 2019 server. We had a proven Cinema 4D and Redshift on-prem production workflow on Windows. Not only that, further integration with managed AD allows us to easily customize our render worker configuration with central group policy, and it also allows us to perform authenticated access to FSX for our artists. And finally, the reassurance of vertical scaling within the P3 and G4 instance families, it enabled us to provide our artists with the confidence that they could continue pushing the limits of their production skills. It was really critical that they were still able to make really striking artistic decisions, knowing that we were fully empowered to render and deliver those results. So engineering decision number 4, when we thought about the ephemeral nature of our render workers, we quickly figured out using Deadline and AWS Spot instances was really in the critical path to ensuring the solution was cost viable. And the good news is Deadline and AWS Spot integration is out of the box functionality, and that uses the Deadline Spot event plugin. And we found it to be a very low friction exercise to get both Deadline and AWS Spot partnered up. Now, the diagram above demonstrates in its simplest form how we create local groups in Deadline to map to specific Spot Fleet requests defined in the Spot Event plugin. So here you can see the artist submits the render job to a specific Deadline group, and a corresponding Spot Fleet request is submitted by the Spot Event plugin. Now, this JSON configuration can simply be exported from the AWS console, and we can paste that straight into the Spot Event plugin. So when our Spot Fleet is up and running, how are we monitoring and how are we managing that Spot Fleet? Well, fortunately, there's a management resource called Resource Tracker to ensure that your instances stay healthy or are rebooted if they're not healthy. It can also terminate parts of a fleet if need be. This again is all out of the box functionality, and the supporting serverless infrastructure is provisioned by Deadline. This is essentially a degree of auto healing for your Spot Fleets. Now, the addition of an idle shutdown timeout was particularly useful for us. So when all of your jobs have finished, your Spot Fleet instances will be shut down within a configurable time. That's really great when you just want to let it run if it's late at night and go to sleep and prefer not to wake up to a big EC2 bill. So another really crucial decision to be made was how we were going to be licensing the solution. And this wasn't how we were going to license Deadline itself, because Deadline licensing is free when running your render nodes on EC2. But ultimately, we had third-party products which had relied on traditional licensing models. So if we were going to be able to dynamically provision Spot Fleets to meet our render compute requirements, we figured it was really important that you always had enough licensing to do so. So all of our rendered workers are configured to use third-party usage-based licensing. So we can consume C4D and Redshift license by the minute, and we can pay for that by the number of hours rendered. And as each frame is processed, the render task will open a connection to the Deadline usage-based license server, which will securely proxy that request for a license to the ThinkBox Cloud license server. Now, this is on a frame-by-frame basis, so you only ever pay for the time the GPU is rendering the frame, and then the clock stops. Now, purchasing on-demand render time provides a great deal of comfort for us, because essentially we are completely free of licensing decisions when we choose to horizontally scale our resources out. And this has positioned us really well for running the platform as a shared service. So now onto some results for a single 4K render using both P3 and G4 instances with all GPUs processing the single frame. Now, as you can see, there's an almost linear reduction in render time as we proportionally increase the number of GPUs. Now, bear in mind, however, this is the pure render time on the GPU, and this doesn't factor in there are other CPU-based processes happening at the start of the render on each node. For example, we get Redshift texture conversions, we're obviously loading Cinema 4D files and initializing renderers. Now, these are primarily CPU-based processes, and some are single-threaded, so these all have the potential to increase the initial frame render times. And there are, of course, additional GPU processes required for each frame, and that depends on what the artist is trying to achieve. And a good example is when we maybe render caustics or light reflections, where we're creating photon maps. And these types of mappings can add a minute or more to the potential frame render time, depending on the complexity. But with all these challenges, what was really abundantly clear to us was that the P3 instances gave us the resource to tackle these, particularly when delivery time was the key metric. And the G4 provides us with a cost-efficient compute and we're typically using them for rendering test frames or renders at lower resolution and less complex scenes. So on to some 600 frame renders. When we took the P3 16 large to work on some of our most demanding production workloads, we had some great results. Now, through Deadline, we provisioned a Spot fleet of 20 P3 16x large instances. Now, that amounts to 160 V100 GPUs, and as you can see, just over 819,000 CUDA cores. And as the job complexity increased, we predictably saw an increase in render time. And it's only working in close collaboration with our creative teams and artists that we continue to define our baseline compute requirements for varying levels of scene complexity. Typically, they will know of specific elements in the scene that have the potential to increase the frame render times, but ultimately, we know we have both vertical and horizontal scaling to address those requirements. Crucially though, this has been a real game changer. We've been able to embrace a new level of agility, which is free from the physical constraints of racking and stacking, and we can harness just the right amount of compute resource for just the right amount of time. And there are, of course, some optimizations we picked up on this journey, which we found to be useful. So firstly, we can pre-convert our textures so Redshift already has the format it is expecting. If you don't do this, then it's going to do this for you anyway. And that time across a Spot fleet can add a substantial lead time to starting a render. For CUDA apps like Redshift, if you're using Windows, and particularly G4 instances with a grid driver, then put the driver into TCC mode. This optimizes the GPU as a compute resource, and it also bypasses WDDM. We can also optimize GPU clock speed. Both the NVIDIA T4 and the V100 can run at a number of different clock speeds, but by default won't be configured to the maximum. We can play around with GPU affinity, and this is a deadline configurable, and it's the process of taking on more than a single frame per instance, and then processing it with a subset of the available GPUs. Ultimately, because there are CPU processes happening during frame render, if we have some spare CPU headroom, then we should exploit this to get the best CPU-GPU performance ratio. And finally, in CloudWatch, we need to keep an eye on FSX throughput capacity when we horizontally scale. There's a lot of reads and writes going on, and we can always adjust our throughput capacity in our CDK code. We can simply go into our stack and redeploy that stack if the need arises. So these pretty much wrap up my part of this session. So thank you everyone for watching, and I'll hand you back to Asghar to wrap up.
Thank you, Andy. Further to rendering faster, the Cloud Render Farm provides us with broader business benefits. Tactically speaking, we can scale up and out and pivot between CPU and GPU instances. This removes the computational ceiling from the render farm. You can render as fast as you can afford to, and this allows artists to create more freely without compromising their vision. We can build and replicate the environment programmatically and on demand. This enables portability and to provision and release resources as we need them to minimize cost. The environment also has a fully remote lifecycle. It was designed, built, and operated remotely. Strategically speaking, we attained our vision. This project occupied a visionary status and scratched the innovation itch that great engineering teams have, and it was a big milestone in our cloud adoption and excellence strategy. The solution is well architected, incorporating infrastructure as code, auto-healing, and meaningful use of Spot services, a powerful combination of modern cloud practices. So what's next, and where are we going? We now have the capability to render in the cloud and are focused on continuous service improvement and wider adoption in the business, which includes improved cost tracking and predictability for better cost modeling and chargeback, a self-service utility, meaning an on-demand platform service shared by multiple teams, and finally, our new vision, Cloud All-In, which is to contain the end-to-end production workflow in the cloud.
Thank you so much, Asghar and Andy, for sharing those insights. If you're interested in learning more about running graphics, VFX, and rendering workloads on AWS, you can access the Studio in the Cloud site at aws.amazon.com/media/production, or you can go directly to building your first RFDK app at docs.aws.amazon.com/rfdk. And with that, we'd like to say thank you very much for tuning in today, and please remember to fill in the session survey.